Imagine a star system. You'd probably think of a giant star being orbited by smaller planets. And generally speaking, this is the standard for star systems across the universe. However, solar systems come in many shapes and sizes. Could it be that there are planets out there that are bigger than the star they are orbiting? And leading on from that, how big can planets get? What's the biggest one that we know of? First of all, let's define one point. When we talk of big, what we are actually referring to is the volume of an object, not its mass. In order for a star to be a star, it has to be over a certain mass, namely 0.08 solar masses, or 8% of our Sun's mass. Below this threshold, the object is classified as a brown dwarf, because it didn't become massive enough for nuclear fusion to take place in its core. Lower masses than brown dwarfs are simply planets, asteroids, and dust. So, the minimum mass of a star is 0.08 solar masses. Is there also an upper limit? Theoretically, the most amount of mass a star can attain is about 150 solar masses, before models suggest it would lose its stability. Although, interestingly enough, there are some stars in existence that seemingly contradict that theory, like the most massive star that we know of, R136A1, which is estimated to be around 300 solar masses. Regardless, just because a star is massive doesn't mean that it's big. Some of the densest stars in existence, neutron stars, are 1 to 2 solar masses and can be only 30 kilometers across. Imagine fitting the vast mass of our star, an object so huge that it dwarfs Jupiter considerably, let alone us, and squeeze up to 2 of these in a space the size of a large city. While these stars are tiny volume-wise, they easily have enough mass to host a grand solar system that could stretch far beyond our own. We have discovered exoplanets around neutron stars. However, due to the detection method used to discover them, we can only really define their mass, not their radius. It would make sense though that these planets are many times bigger than the tiny star, as we have asteroids in our solar system which can be hundreds of kilometers across, let alone planets thousands of kilometers across. White dwarfs are another example of tiny stars that likely have larger planets orbiting them. White dwarfs are the remnants of red giant stars that weren't massive enough to become neutron stars in a supernova explosion when they reached the end of their lives. Instead, they shed their outer layers in a planetary nebula, leaving behind the core of the star, or what is known as a white dwarf. Nuclear fusion does not take place in a white dwarf, meaning their luminosity comes solely from stored thermal radiation. This makes them quite dim stars, and they only get dimmer over time. Planets that would have survived the star's evolution from main sequence to red giant to white dwarf could well be larger than the small remnant white dwarf, which is typically the radius of Earth. There has just been confirmation of such a planetary system thanks to the TESS Observatory. An exoplanet known as WD-1856b. What's remarkable about this system is that the planet orbits the white dwarf relatively closely, meaning it survived the star going through its red giant phase. The red giant phase would have easily enveloped where the planet now resides, so this means the planet must have fallen or scattered into this orbit after the event, perhaps thanks to the gravitational influences of the star's other undiscovered planets, or even from nearby stars that the white dwarf is gravitationally bound to. In any case, it's an incredible system indeed. When it comes to main sequence stars, planets larger than them are tricky to find too. We believe that main sequence stars make up the majority of stars in the universe. These can be very big objects, as internal pressure from the reactions in the core keeps the radius large. We'd have to look for stars right around the dividing line between brown dwarfs and red dwarfs to find a main sequence star small enough to host a larger planet. Remember, the difference between a brown dwarf and a main sequence star is whether nuclear fusion takes place in the star's core, which we believe happens above 0.08 solar masses. And we also believe the dividing line between a planet and a brown dwarf is around 13 Jupiter masses. So, one of our best bets to find a tiny star with a large planet is looking around the red dwarf VHS 1256-1257. Its exoplanet is one of the few exoplanets to be discovered using direct imaging. Its host star is dim enough, the exoplanet is far enough away from the star, and the exoplanet big enough to be seen simply by using a powerful telescope. Unfortunately though, this means that while the mass of the exoplanet has been determined, we can't know of its radius for sure. However, this is one of the most likely candidates that we know of. Also, because of the margins of error involved, it could well be that either or both objects are brown dwarfs, meaning we can't say if this is truly a star and planet system. So while we don't have definitive proof of a planet being bigger than its host star, we have found some promising candidates, and there's almost certainly cases out there that we haven't found yet. Some of the smallest stars out there have a radius of roughly 70,000 kilometers. Some of the biggest planets out there can be double or triple that. Which leads on to the final question I wanted to cover here. What is the biggest exoplanet that we know of? The answer is most likely GQ Lupi b. It is another directly imaged exoplanet, which again means we don't have a good grasp on its physical characteristics. From the margins of error involved, it could be a brown dwarf, but it's probably the largest exoplanet that we know of. Scientists have estimated its radius to be 3 times the size of Jupiter, but again there are margins of error involved. Other contenders to this throne would be DH Tauri b and ROX 42BB. So there we have it, some of the biggest exoplanets that we know of. And it's certainly feasible that somewhere out there is a planet bigger than its host star.